So good morning to all of you. This is Rama Krishna from KL University. We are now heading towards our second lesson on basics of convection and radiation. In the last session we have seen the difference between the heat transfer and thermodynamics course and what are the different modes of heat transfer like conduction, convection and radiation. And few details of conduction we have studied, that is the Fourier's law of conduction, and we have defined what is thermal conductivity and how the materials exhibit the property of conduction, etc. Now in this session we are going to see what is convection and what are the different types of convection and what is the difference between forced convection and natural convection, and what is the fundamental law of convection, and what is convective heat transfer coefficient, and on what factors the convective heat transfer coefficient depends, and ultimately how to estimate the heat transfer by convection mode. Convection is the mode of heat transfer which occurs due to the motion of molecules carrying energy from high potential zone to low potential zone. This occurs basically in two ways. One is natural or free convection and other one is forced convection. For example, if you have a hot plate hanging in air at room temperature, then the air molecules will come in contact with the plate surface. They absorb heat from the plate and then they move away, giving way to the cold molecules again to come in contact with the plate and absorb heat. So this motion of air molecules carrying heat energy from the high temperature zone, that is high surface at high temperature, into the environment is called convection mode. Have a look at this diagram. When you keep water in a pan on a stove, the bottom surface temperature rises and then the water molecules coming in contact with this hot surface carry heat energy, move up, and in the process of rising they interact with other cold water molecules. Again they lose heat, they will come back, they touch the surface, again they absorb heat and they move up, and that circulation goes on. This mode of transfer of heat energy by means of motion of the molecules carrying heat from high temperature zone to low temperature zone is known as convection. Say a plate like this. When it is kept in still air, the air molecules will come in contact with the surface of the hot plate. The temperature increases, they become warm, they lose their density, and because of the buoyant force acting on them, warm air will rise up. Again, the place is occupied by the cold air. It will also start picking up heat from the surface. It moves up. Like that, heat is being carried from the surface to the environment due to the motion of air molecules. And another example is, you keep a hot coffee on the table in still air. It gets cooled by natural convection. The air molecules coming in contact with hot surface of the coffee gets heated up, their volume increases and hence they lose density, and due to buoyant action the lighter molecules move up carrying heat energy and the place is occupied by another cold air molecule. The process continues. Suppose instead of keeping the plate in still air, if you switch on a fan and force the air molecules to move over the surface, then the cold air molecules, while moving over the surface, are forced to pick up the heat energy from the surface, and that kind of heat transfer is called forced convection. Here, the fan creates the external driving force to make the molecules move over the surface. We have seen the example of coffee leaving on the table. Instead of leaving the coffee on the table to cool it on its own, if you switch on the fan to cool the coffee, thus forcing air molecules to move over the hot surface, carrying the heat energy, then that kind of convection is called forced convection. Like this, if you leave a coffee on the table without fan, it is called natural convection. If you switch on a fan and blow air to cool the coffee at a faster rate, we call it as forced convection. Instead of keeping the coffee in the cup, if you pour it in saucer, it gets cooled at a faster rate because the area of contact between the surface and surrounding air molecules increases. Therefore, the heat transfer by means of convection is directly proportional to the area of its exposure, and of course the temperature difference between the surface and surroundings. For example, if the surface temperature and surrounding air molecules are at same level, then there will be no heat transfer. With increase in temperature, the rate of heat transfer goes on, increases. Similarly, with increase in surface area, the rate of heat transfer also increases. So Q is directly proportional to area temperature difference. If you remove the proportionality, you have to introduce a constant called convective heat transfer coefficient, H. So Q is equal to HA delta T. We have seen that Q by A is heat flux. So we can say that the heat flux is directly proportional to temperature difference between the surface and surrounding medium. This is what is called Newton's law of cooling. So Newton's law of cooling states that the rate of heat transfer by convection is directly proportional to surface area exposed to the surrounding medium and temperature difference. So Q equal to HA delta T, where delta T is the temperature difference between the surface and surrounding fluid, TW minus T alpha. Suppose I hang a cylinder in the air, the air molecules will come in contact with the entire cylindrical surface area. So the area we have to take 2 pi RL, where R is the radius and L is the length of the cylinder. And of course, pi r square at the top and pi r square at the bottom will also play a role in losing heat transfer by means of convection. If you take a sphere, when you put a hot sphere in cold water, the cold water molecules will come in contact with the entire surface of the sphere and takes away heat from it by means of convection. So the area which we have to account there is 4 pi r square. So A in case of convection is the exposed surface area to the medium. Q is equal to HA TW minus T alpha indicates that H is equal to Q by A TW minus T alpha, where Q is in watts, area is in meter square, and delta T either in Kelvin or degrees Celsius. So the unit for convective heat transfer coefficient is watt per meter square Kelvin. The convective heat transfer coefficient is nothing but heat transfer ability of a fluid per unit area and per degree temperature difference. When you make A1 TW minus T alpha 1, H will become Q. So convective heat transfer coefficient is the ability of a fluid to take away heat from a hot surface or pass on heat to a cold surface. This convective heat transfer coefficient is a very complicated parameter depending on the density of the fluid, the velocity of the fluid in case of forced convection, or the buoyant force in case of natural convection, the viscosity of the fluid, the specific heat of the fluid, the thermal conductivity of the fluid, and the characteristic dimension of the object. Instead of air, if you pour water on a hot surface, it gets cooled quickly because the density of water is more than that of density of air, and specific heat of water is more than that of specific heat of air. Instead of blowing air at 1 meter per second, if you blow air over a hot surface at 5 meters per second at a faster rate, the heat is removed. So it also depends on the velocity of the medium and thermal conductivity of the medium, viscosity of the medium. So it's a very, very complicated parameter. Convective heat transfer coefficient depends on all these factors. How to identify the convective heat transfer coefficient or how to evaluate the convective heat transfer coefficient is the major task which we are going to take up in the chapter on convection. Time being, in the fundamentals of convection, we just understand the role of convective heat transfer coefficient and how to evaluate the heat transfer by means of convection if we know the value of H. So if H is given, surface area is known, temperature difference between the surface and surrounding fluid is known, you can evaluate the rate of heat transfer by using Newton's law of cooling. As I said, the convective heat transfer coefficient strongly depends on fluid properties like dynamic viscosity, thermal conductivity, density, specific heat, and the fluid velocity. And of course on the geometry and roughness of the solid surface, which is indicated by this L, characteristic dimension. When compared to natural convection, in forced convection, we all know that the rate of heat transfer will be high. Suppose I want to cool the coffee at a faster rate, I will blow air with my mouth over the surface. So which indicates that the heat transfer coefficient under forced convection is more because there is no change in surface area, there is no change in temperature difference, but Q is increasing means the H value invariably should increase. So when compared to free convection, in forced convection, the value of H is high. When compared to gases, liquids are having more ability to convect heat that is stable. So under free convection, the value of H for gases is around 2 to 25 watt per meter square Kelvin, and liquids exhibit between 50 to 1000 watts per meter square Kelvin. In case of forced convection, gases can exhibit the convective heat transfer coefficient from 25 to 50 watts per meter square Kelvin, and liquids exhibit 50 to 20,000 watts per meter square Kelvin. And in case of phase change, that means either during boiling or condensation, we all know that there is no temperature difference, but transfer occurs, an indication that the value of H is very high, in the order of 2,500 to 1 lakh watts per meter square Kelvin. So in case of convection, the rate of heat transfer Q is determined by using Newton's law, Q equal to HA delta T.